You have believed your entire life that the history of technology is a series of random discoveries and brilliant loners. But when you place the blueprints of 8 objects from 2 continents on the same table, the theory of randomness crumbles to dust. In Manchester, a standard is introduced that subjugates all factories in the world. In London, a tunneling technology is perfected that won't change for a century and a half. In Chicago, an entire city is lifted on thousands of jacks, the manufacturing factory of which has been erased from all archives. And in Scotland, a bridge is built based on mathematics that officially did not yet exist. How did it happen that in different countries, in different decades, completely unrelated people solved problems with the same handwriting? Why do we see the same thing everywhere? A mature solution on the first attempt, the absence of prototypes, and the instant disappearance of all documentation about the clients. This doesn't resemble evolution. It looks like the deployment of a ready-made kit. Official science calls this the Industrial Revolution. But the facts indicate that this was a covert installation of a control system that still governs the world today. The main question is, whose hands were responsible for building the framework of the 20th century when the 19th had not even finished? There is a question that I struggled to formulate precisely for a long time. It's not who built it, nor why is it hidden. It's a different question, a more uncomfortable one. Why did the 19th century need the precision, speed, and power that it could officially neither apply nor explain? Look at the standard textbook on the history of technology. There is always the same illustration. The lone inventor or a small team, years of failures, gradual improvement, finally a breakthrough, recognition, the next step forward. One step at a time. Technology grows from itself. Logical, convincing. But sometimes something appears that doesn't fit into this picture. A tool whose precision will only be needed in 140 years. A tunnel, the principles of construction of which will not change for a century and a half. A network of pipes designed in such a way that in 100 years it will be suitable for a completely different technology. A bridge calculated with precision for mathematics that has yet to exist. These are not just anomalies. They are anomalies with the same structure. And to see it, one must look not at the biographies, but at the chronology. Look at the specific numbers. The first fully automated metalworking plant, 1803. The first underwater tunnel with a tool that has fundamentally remained unchanged for a century and a half, 1825. A measuring device with the accuracy of a laser interferometer, sold commercially, 1855. A distributed energy network with an architecture from the electrical era, 1883. Take for comparison several well-known technologies. Bell's telephone, the first call in 1876, followed by another 10 years of improvements to achieve reliable communication over several kilometers. The steam locomotive, from Trevithick's first working model to Stephenson's trains, 25 years and several generations of complete redesigns passed. Radio, from Hertz's experiments to the first practical transmission, 18 years and several fundamental concepts were developed. Normal technology relies on iterations. Our 8 projects deviate fundamentally from this scheme. Brunel's tunnel applies the shield principle on the very first construction site, without prototypes. The pneumatic mail system resolves all sealing and pressure challenges from the initial version. Baker's cantilever design achieves jointing of spans with deviations of just a few millimeters right from the start. Where are the iterations? Where are the half-rotten first versions? Where are the dead-end branches? There is nothing. Mature solutions emerge immediately. It's a signature style. Let's start with a question that engineers still can't resolve definitively. In 1855, an instrument was made in Manchester, small, with a working table, made of cast iron. Externally, it was nothing special. No electricity, no lasers, no digital scales. But this instrument could measure with an accuracy of 1/1,000,000th of an inch. That's 25 nanometers. For comparison, modern laser interferometers used in microchip manufacturing operate in approximately the same accuracy range. Only they have lasers, vacuum chambers, and digital signal processing. But Joseph Whitworth in 1855 had only mechanics, cast iron, a fine-pitch differential screw, and the tactile sensation of contact through a ball held between two surfaces by its own weight. At the exhibition of 1851, Whitworth demonstrated to the public how his machine registers the expansion of metal from the touch of a finger, the warmth of the hand, and the device records it. The spectators thought it was a trick, but among the audience were not only journalists. There were delegations from industrial companies, representatives from military departments, people who viewed it not as an attraction, but as a tool that they needed. The only question was, for what exactly? Now let's look at the problem from a different angle. The locomotives of that time had a manufacturing tolerance of a few hundredths of an inch, an industrial standard of the era. For this, a precision of 1/1,000,000th is excessive by 2 orders of magnitude. But if the tool is not needed for mass production, it does not mean that it should not be used. It means that the problem exists beyond the realm of public production. The most obvious explanation is that Whitworth was simply doing science for the sake of science, like a solitary scientist. But that's not the case. His machines were not just unique laboratory instruments. They were sold, commercially, to industrial companies throughout Britain. This means that someone was buying these machines and using them. Where? For what purpose? What production tasks required the precision of a laser interferometer in the era of coal and steam? The product catalog of the Whitworth firm has been preserved. It includes names of buyers, albeit only partially. Interestingly, among them are not only machine-building factories, but also several institutions related to the Admiralty, a number of cannon factories, several arms manufacturers, which in public documents do not specify exactly what they produced with precision to 1/1,000,000th of an inch. A complete list of buyers is absent from the public archives. This in itself is a detail. Alongside the measuring machine, Whitworth promoted a thread standard known as BSW, British Standard Whitworth. And this is where the real story begins. This standard became global. Any cannon, any locomotive, any cable coupling, any ship bolt in the 19th century either conformed to Whitworth's standard or it did not. There was no third option. One standard, one person, the whole world. Think about this practically. Not in a political sense, but in a mechanical one. If a cannon is being built somewhere on the planet, its breech mechanism is held together by bolts. If those bolts are not to Whitworth specifications, the cannon cannot be repaired in the field with a standard part from another factory. The military convoy does not carry a screw-cutting machine. It carries spare bolts. If the bolts are incompatible, the cannon is grounded. Without a single thread standard, the military machine halts from any breakdown anywhere except at the original factory. Whitworth resolved this issue. One bolt, one standard. The entire world is interchangeable. There is another perspective that is rarely discussed. The standard is policy. Whoever establishes the standard knows what is being produced and how precisely it is interconnected. A factory in St. Petersburg, Boston, or Calcutta, in order to trade with British buyers, must adopt the Whitworth standard. This means that any new production, wherever it may arise, is integrated into a system from the very first bolt, the parameters of which are defined in Manchester. Not by decree, not by contract, simply because otherwise the parts do not fit. But there is one more point that historians usually overlook. To create a measuring tool with an accuracy of 1/1,000,000th of an inch, you need a standard that is even more precise. Otherwise, where do you get a starting point? Where do you find the surface against which everything else is measured? Whitworth solved this paradox through the method of 3 plates. 3 surfaces are mutually ground against each other, and as a result, all 3 become perfectly flat, more accurate than any initial tool. Logically, flawless. But technically, this requires an existing culture of precision metalworking, existing hands that know how to do it, existing machines that maintain the tolerance. Whitworth did not invent precision. He documented it. He formalized it into a standard. These are different things. The culture of precision machining existed before him. It was passed down through apprenticeships, through production lines, through generations of craftsmen who knew how to keep tolerances. Whitworth gave this culture a name, and thereby made it exportable. Here's another fact that rarely makes it into mainstream textbooks. The BSW standard was adopted not only by British factories, but also by factories in India, Australia, and Canada. In other words, everywhere the industrial infrastructure of the British Empire spread. This meant that any part manufactured in Calcutta was compatible with a part from Manchester. A military engineer, finding themselves anywhere in the empire, could repair weapons, machinery, or bridges using local spare parts. The logistics of war had changed, but the standard didn't stop at the empire. American factories also adopted BSW as a de facto norm in the 1870s, because otherwise they couldn't trade with British buyers. So one man in Manchester by 1860 controlled the compatibility of industrial production across 4 continents. There is one fact that is worth recalling here. 50 years before Whitworth, in the year 1803, a factory appeared at the Portsmouth shipyard. 45 machines, made entirely of metal, 22 types, all operated by steam engines through a system of shafts and belts. 10 workers on these machines replaced 110 skilled craftsmen. The parts were made to be interchangeable. Each pulley fit each housing of the corresponding size without any adjustments. This was the world's first fully automated factory complex, 1803. And here's the question. Who made 45 of the most complex precision machines for this factory? The answer is Henry Maudslay, the very man who later employed Whitworth. It was on the Portsmouth Machines project that Maudslay perfected the lathe with a screw-cutting mechanism, thereby standardizing the production of threads half a century before the official standard. Whitworth came to him as an apprentice. He left as a guardian of the culture of precision, which he would later name. And here is what is remarkable in this line. From Maudsley to Whitworth is 30 years. From Whitworth to the Chicago Serial Jacks is another 30. Half a century of continuity. The culture of precision passed through hands, through workshops, through orders. And by the mid-19th century, it became embedded in the production infrastructure of 2 continents. Not through textbooks, through practice. Now, let's go underground. Ask yourself a simple question. By the year 1825, do you know of even one precedent for constructing a tunnel under a navigable river in unstable quicksand? No, such a precedent does not exist. Not in Britain, nowhere in the world. Engineers knew why this was considered impossible. Quicksand under a river behaves like a liquid under the pressure of water above. Any excavation of soil without immediate support leads to an instant collapse. No formwork holds. No method of reinforcement works. The task was deemed closed. And yet, Marc Isambard Brunel does not approach his clients with the words, "We will try." He comes with a ready engineering solution, a tunneling shield that replicates the biological principle of a marine worm. Here's how it works in detail. The shield is not just a frame. It consists of 36 separate working cells arranged in a rectangular array. Each cell is a kind of trench with a board at the front. The worker opens one board, digs out precisely 4 inches of soil, and then closes the board. Then the next one. Then the next one. He never exposes the entire face of the excavation, only one point at a time. This is the principle of the marine worm. Teredo nivalis does not gnaw at wood with an open front. It drills a tube, immediately reinforcing the walls with its secret. Brunel translated biology into engineering, not metaphorically, literally. The key element is synchronicity. 36 workers who must move their sections forward evenly. Otherwise, the frame becomes skewed and the shield gets stuck in the ground. This is another version of the same challenge as in Chicago. Coordinating a multitude of people, each of whom sees only their specific cutting point. The same whistle system. The same principle of 1 rotation per signal. Different countries, different decades, one and the same operational solution. This is not just a coincidence of methods. It means that someone between the years 1825 and 1850 systematically solved the same problem: how to manage a large number of people in conditions of limited visibility with a high cost of error. And they solved it in the same way. In London, under the river. In Chicago, beneath the buildings. 1825, London. A tunnel is beginning to be dug beneath the River Thames. The first underwater tunnel in human history. Marc Isambard Brunel is the chief engineer. Bricks are sinking into the river. Up to 70,000 bricks a week. The shield moves forward, 4 inches per operation. Try to imagine the conditions. The Thames of that time is not the river you see today. It was an open sewage system for a 2 million strong city. All the garbage, all the wastewater, all the refuse flowed directly into it. Beneath this river, just a few meters from the ceiling of the tunnel, this current was running. When the shield cracked, and it did, London's sewage poured through the ceiling. The workers stood knee-deep in it. Hydrogen sulfide, methane, typhus from every second puddle. The construction lasted 18 years. The tunnel was flooded 5 times. Workers lost consciousness from hydrogen sulfide. One of the floods nearly swept away Isambard Kingdom Brunel, the son of the chief engineer, who was also working on the site. He was pulled out unconscious but survived. They spent £630,000. In today's terms, that's about $75 million. And what was the result? A pedestrian attraction with shops inside the arches. The eighth wonder of the world, as the newspapers called it. Tourists paid pennies, walked under the river, bought souvenirs from vendors lined along the walls. No freight, no horses. The ramps for them were never built. Not a day of commercial profit until the tunnel was bought by the railroad 20 years later. Wait. The state funded this project as an object of national importance. 18 years, with 5 floods, without a single day of profitability. For the sake of a pedestrian attraction? Historians usually say, well, it was a demonstration of technology, a proof of concept. They showed the world that it is possible to excavate under a river. Okay, let's say. Then why did the government pay for this proof of concept with funds from the fleet and treasury rather than private investors' money? And who exactly insisted on the status of national importance? Who was it that needed to know that a secure corridor could be laid under any city, beneath any river, under any strait? Brunel's tunneling shield has fundamentally remained unchanged for a century and a half. It was with this type of shield that the London Underground was constructed in the late 19th century. Its principle was also used for the construction of the tunnel beneath the English Channel in the 1990s. And here's what's important. After the Thames, military and civil planning changed irreversibly. Now any strategist could assert with engineering calculations in hand that a secure corridor could be laid under any city, under any river, under any strait. This knowledge was worth more than the tunnel itself. There is one more detail that is rarely mentioned. While the tunnel was being built, it was used as an attraction and a source of income. Banquets were held right in the under-construction tunnel. Tickets for tours to the excavation site were sold. The construction was illuminated with gas lamps, attracting wealthy Londoners to come and see it. A state project that officially did not pay for itself nonetheless generated cultural excitement and public interest. The tunnel under the Thames became a symbol of what humans can achieve by penetrating beneath the riverbed and emerging alive on the other side. This shift in what people considered possible was just as significant as the technology itself. The next object transports us to an Irish bog, and it looks nothing like what we discussed, because up until now, the discussion has revolved around things that could logically be justified by considerations of military or trade strategy. A tunnel is a corridor. A thread standard indicates control over production. But the next object is a telescope, a tool for observing the stars. What exactly is strategic about the stars in the year 1845 is not entirely obvious. That's what's interesting. County Offaly, Ireland, 1845. The year when the potato famine begins in Ireland, claiming the lives of 1 million people. The country is devastated. People are fleeing. At the same time, the construction of a telescope is finishing at the private estate of Birr Castle. Not just any telescope, the largest in the world for the next 72 years. A pipe 17 meters long, a mirror with a diameter of 183 centimeters. The weight of the mirror is nearly 4 tons. The material is speculum, an alloy of copper and tin. The pipe is suspended between 2 stone walls that are 12 meters high. The telescope weighs 12 tons, but is balanced by a system of chains and counterweights such that one person can move it. This was built by Lord William Parsons, the Earl of Rosse, a self-taught metallurgist, without professional education in this field, without government funding, without assistance from academic institutions. For a single casting of the mirror, it was necessary to burn 2,000 cubic feet of peat from local bogs. The mold for the casting was invented by Rosse himself, a base made of thousands of strips of wrought iron placed on edge, allowing gases to escape through microgaps during the pouring process. This solution was Rosse's own engineering invention, which the state observatories, with their professional metallurgists, had not thought of. After the pouring, the mirror cooled in a special furnace for exactly 6 weeks. Any breach of the temperature regime would result in a crack. The mirror would be ruined. Start over. Then, 2 months of polishing on a steam machine that Rosse also built himself, the first steam-powered device in the world for automatic polishing of a parabolic surface. Remember this word, parabolic. A parabolic surface is not just a beautiful curve. It is a mathematically precise shape in which all points on the surface are at a strictly calculated distance from the focus. The slightest deviation and the mirror stops working. Rosse polished 4 tons of metal to an accuracy of fractions of a millimeter. Twice the mirror cracked during cooling, and the entire process had to start over. The construction required 150 tons of cast iron. Now a question. What can you see through a telescope with a mirror of such power in the year 1845 that you can't see with a smaller mirror? There are not many objects. The list of discoveries that were actually made with this instrument is small compared to the expenses. Lord Rosse was the first to prove that the nebula M51 has a spiral structure. This is an important discovery. But it's just one discovery. Here is what is usually left out of this story. Rosse had 3 mirrors. The first cracked during cooling. The second cracked as well. The third survived and became that very giant mirror. But Rosse did not stop after the first failure, nor did he stop after the second. He systematically recorded every attempt, every deviation from the temperature regime, every deformation during polishing. This is not the behavior of an amateur who has taken on a large project. This is the behavior of an engineer who has received a task and carries it out until it is completed. If you think that's the point, fine. Then explain. Why was the technology of a 4-ton parabolic mirror with machine grinding mastered in a private estate rather than in state observatories that had funding, specialists, and equipment? And why did the company Grubb later use the casting methods developed by Rosse to produce military and naval optical instruments? This is what "later used" means. The firm Thomas Grubb & Son in Dublin is not just a random neighbor. Thomas Grubb knew Rosse personally. He worked with him. The manufacturing methods for polishing parabolic surfaces that Rosse developed at Birr Castle were transferred directly to Grubb's company through personal transmission, not publication. By the 1870s, Grubb was already fulfilling admiralty contracts for naval targeting optics. By the 1890s, he was supplying military observation instruments to several European armies. Parabolic lenses for rangefinders and searchlights are direct descendants of the mirror polished in the Irish bog. The technology emerged from the estate without announcements, without patents, through apprenticeship and military orders, without public documentation. A mirror is a parabolic surface. A parabolic surface focuses not only light, It focuses everything that propagates in waves: heat, sound, electromagnetic radiation. The precise technology for manufacturing and polishing parabolic surfaces of such scale serves as a universal foundation for the tools that will emerge in the 20th century. There is one more detail. The Parsons family had owned the Beer Castle estate for several generations. Lord Ross was not just an accidental wealthy man who suddenly needed a large telescope. His father was involved in steam engines. His son later became the first person in the world to build an industrial-scale steam turbine, the very one that ultimately replaced the piston engine in fleets around the globe. 3 generations, 3 engineering breakthroughs, 1 family, 1 estate in the Irish bog. A coincidence is just 1 accident. 3 is a system. Now let's move to another continent. And here it's important to pause. All 3 previous entities are British. 1 country, 1 navy, 1 circle of professional societies. One could say, so what? It's just London's industrial policy. But the following entities are in the United States: an independent country, another continent, different institutions, no visible coordination with Britain, and yet the same handwriting. Mature solutions right from the start. The same resourcefulness that goes beyond the stated task. The same gaps in documents where documents should be. Chicago, 1856. A young city built on a swamp at the level of Lake Michigan. No slope, no sewage system. Rainwater and waste go nowhere. They simply stagnate. Typhus, cholera. Typhoid fever killed an average of 65 people per 1,000 residents each year in Chicago. In comparison, today in developed countries, less than 1 in 1,000 dies from infectious diseases. The city is literally drowning in its own waste. Solution: lift the entire city, physically, along with the buildings. Not to demolish and build anew, but to raise. Residential buildings, hotels, warehouses, pavements, all elevated by a few feet to create a slope for drainage. Hotel Tremont House, 6 stories high, brick masonry. Weight, thousands of tons. Jacks are introduced under the building, thousands of screw jacks. 600 workers take their positions. At the whistle signal, each makes 1 turn. Synchronously. The building rises by a fraction of an inch. At the next whistle, another turn. After a few days, 6 feet upward. Not a single crack in the masonry. Meanwhile, guests are dining in the hotel restaurant. They know the building is being raised. They continue to eat. This is not an isolated incident. It is a systematic operation. The Robbins Building, weighing 27,000 tons, was lifted by 27 inches. 1 city block on Lake Street, measuring 320 feet, was raised using 6,000 jacks simultaneously. 6,000 jacks under 1 block. Consider the logistics of this operation. We need to deliver 6,000 jacks to 1 block, place them under the buildings, deploy 600 workers, train each one to work in sync, neither faster nor slower than their neighbor. No worker can see what the worker 20 meters away from them is doing around the corner of the building. Just a whistle. Just 1 turn. Again a whistle. Again 1 turn. For several days. This is not just an engineering problem. It is a task of managing people under conditions where the cost of a mistake is a crack in the walls of a building or a complete collapse of the masonry. Someone has devised this coordination system. Someone has trained 600 individuals to work as one mechanism. There are no documents regarding this. This is where the real question begins. Not how did they do it, but where did tens of thousands of absolutely identical standardized jacks come from in the 1850s? This is not a blacksmith's handcrafted item. A blacksmith makes one jack over several days. To produce 6,000 identical ones, a factory is needed. A factory with mass production, with standards for threads, with quality control. Such a factory demands precisely the kind of accuracy that Whitworth championed. It requires standardized threaded connections. The official history does not name the manufacturer. It does not show the supply chain. We are told the jacks existed. From where? It is unknown. But look at the logic of disappearance. If it was simply a commercial factory, it would have boasted about it. Journalists of that time loved stories of industrial wonders. The factory that lifted Chicago. That's a headline any newspaper would write. Yet it is absent from all of them. The production trace has been erased, just like the administrative trail of the tunnel construction under the Thames, or the biographical trace of IDS's accounting methods. Now count it for yourself. 6,000 jacks is not a warehouse. It's a production program. Each jack is a threaded pair with a specific pitch, designed for a particular load. To place them under one building and raise them synchronously means all 6,000 units must provide absolutely identical lift with one turn of the handle. A deviation of 5%, and the pressure is redistributed unevenly. The masonry cracks. The building leans. A blacksmith makes one jack over several days. 6,000 identical ones. That's a factory with metrological control. A factory that knows how to work to the Whitworth standard. A factory that is noted nowhere. A subterranean layer has emerged where the raised buildings once stood. What was once the first floor has become a basement. Beneath Chicago lies an entire layer of the old city. It still exists today. Many basements in the center are former ground floors of buildings from the 1850s. Exits, windows, doors, everything is there, buried under asphalt. The city gained a second surface, hidden from view. And it is this fact, the underground layer formed as a result of the operation, that raises the next question. If there is already space beneath the city, what else can be moved through it unnoticed? The question is rhetorical, only if you are not aware of the following object. And it is, strangely enough, not in Chicago, but once again in London. And again, underground. A system begins to operate beneath the city center, which today would be called Hyperloop, only invented a century and a half earlier. Cast iron pipes. Diameter, 33 inches, approximately 80 centimeters. Trolleys on wheels with rubber seals around the perimeter move through the pipes. The seal presses against the wall of the pipe, creating an airtight piston. On one side, a huge fan with a diameter of 6.5 meters is turned on, powered by a steam engine with up to 100 horsepower. The difference in pressure, and the trolley flies. The speed in standard mode is 40 miles per hour. During tests, they reached 70. The wagons weighed up to 3 tons. The system handled sharp turns with a radius of 300 feet and inclines, all without losing speed. Pay attention to the engineering challenge that had to be solved. The cart's seal must press tightly against the pipe's wall. Otherwise, no pressure is generated and speed decreases. However, on turns, the cart slightly shifts from the center of the pipe. At a turn radius of 300 feet and a speed of 40 miles per hour, the centrifugal force pushes the cart against the outer wall. The seal must compensate for this displacement while remaining airtight. This problem was solved in 1863 with rubber seals in the very first version of the system. The official goal is to transport mail bags between train stations and postal centers in London, to bypass traffic, to deliver mail faster. During the tests in the tube, people were taken for a ride. Journalists described the experience as thrilling, a dark tube, an increasing roar, and then a sudden stop at the destination station. Through a tube that was 80 centimeters in diameter, at the speed of a courier train, in complete darkness. The system operated from 1863 to 1874. It was not closed due to technical issues. Engineers specifically noted this in the documents. It was shut down because the Postal Service did not want to pay for excessive speed. Letters were already being delivered. Why pay more for something that arrives faster? But wait, for whom is it excessive? A letter delivered in 10 minutes instead of an hour is not a luxury. It's a management tool. It's the ability to obtain information and make decisions earlier than a competitor can. The speed of communication is power. Why would a postal official shut down a system that empowers those who control it? Unless those who use the system already had another, faster channel. And the excess pneumatics were simply unnecessary. The pipes remained lying under London. They were discovered during roadworks in the 1920s. They were found again in the 1980s. They are still there. An interesting detail, rarely mentioned in this context, is that a nearly exact replica of the London system was being constructed in Paris around the same time. The company, Société Générale des Tubes Pneumatiques, was behind it. The same pipes, the same logic, the same scale. The Paris pneumatic network operated from 1866 to 1984. It was closed with the same phrasing, excessive expenses. The pipes were also left behind. They still lie under Paris. Two capitals, the same solution, the same fate. The same ambiguity in the documents regarding why this infrastructure was built with excess capacity that the Postal Service never utilized. Now look, the system's capacity significantly exceeded the actual needs of London's postal service in the 1860s. The tubes were designed with a surplus. They could move cargo, people, anything, at speeds that were simply unbelievable for that time. The network was designed as if for a different scale of tasks that never publicly materialized. Or it has arrived, but not publicly. Look at how exactly the story of the pneumatic system came to an end. Not gradually, abruptly, with one administrative decision. The system was 11 years old. It had been functioning. They simply shut it down and left it lying under the city. You don't treat a failed experiment like that. With a failed experiment, you dismantle the equipment and sell it for scrap. An untouched infrastructure is left behind for only one reason: to have the possibility of returning. And underground London at that time, another system was already operating. It was unseen by passers-by. It produced no smoke and made no noise. It simply existed everywhere. 1883. The London Hydraulic Power Company is founded. The company lays a network of cast iron pipes beneath the city. The total length is 180 miles, nearly 300 kilometers. Water continuously flows through these pipes under a pressure of 800 pounds per square inch. That's 55 atmospheres. Why? Look at what was powered by this pipe. The elevators in the Bank of England, the very ones that descended into the vaults with gold bars. Cranes in the ports, the mechanisms for raising the spans of the Tower Bridge, the same ones that lift the sections. The rotating stage of the Palladium Theatre, fire pumps throughout the city, printing presses in the printing houses. All of this was supplied by one pipe. Before the widespread use of electricity, this was the only way to provide industrial power to any building without its own steam engine. Connect to the pipe, and you have power. Invisible, without smoke, without a boiler, without maintenance. Just connect. Think about what this means in terms of control. If all the industrial power of the city comes from one pipe, whoever manages the pumping stations controls everything. The lifts in the Bank of England stop because the pressure has dropped at the central station. The cranes in the port shut down. The fire pumps fall silent. This is not just convenient infrastructure. It's a switch. One switch for the whole city. But the most remarkable thing is not in the control mechanism, but in the fact that this infrastructure has survived 4 technological eras: the steam, electrical, oil, and digital ages. The water network of 1883 has become the fiber optic route of the 21st century. Not because it was planned that way, but because the pipes were laid with a surplus that lasted for 140 years. To maintain a constant pressure, hydro accumulators were installed at pumping stations. Imagine a vertical cylinder with a piston. On the piston, there is a load weighing hundreds of tons. Water is pumped in from below. The piston rises. If the pressure drops in the network, the piston pushes down, maintaining the pressure. This is a simple mechanical principle, but the scale is industrial. In winter, the water in the pipes was heated to prevent freezing. The system survived everything. The steam era, it survived. The gasoline era, it survived. The electric era, it survived. It closed in 1977, 94 years of operation. Here is a specific figure that is important. In 1883, when the pipes were laid, the average design lifespan of industrial infrastructure was 20 to 40 years. Hydraulic pipelines for specific factory needs were designed for 20 to 25 years at most. 94 years is 4 consecutive design lifespans. Either this is exceptional luck with the quality of the cast iron, or someone initially had a different time horizon in mind. Just think about the scale of the maintenance. 180 miles of cast iron pipes underneath the city. Every joint, every valve, every connection had to withstand 55 atmospheres of pressure, constantly, without fluctuations, without leaks. A leak in such a system is not just a dripping faucet. At 55 atmospheres, the pressure strikes like an industrial cutter. In the summer, the thermal expansion of the cast iron altered the geometry of every connection. Such a network had to be memorized. Every meter, every turn, every history of each pipe. Generation after generation of workers passed down this knowledge. 94 years. Is it a coincidence? or a design principle. Reserve is not wastefulness. Reserve is intention. Now let's cross the Atlantic. St. Louis, 1867. A man named James Eads receives a contract to build a bridge over the Mississippi. Eads has never built bridges in his life. His specialty is raising sunken ships. He knows the rivers, knows the currents, knows how the riverbed is structured. But bridges? No. This is his first. This is what needs to be examined here. The steel that Eads will require for the supports, chromium alloyed, belongs to a European technology from the 1860s, British and French metallurgy. The caisson method, as applied by Eads, had already been used in Europe several years prior during the construction of supports for several bridges over the Thames and the Rhine. The cantilever principle for large spans was thoroughly discussed in the journals of the Institution of Civil Engineers, the very ones that American engineers systematically read. Eads' official biography, up to the first bridge, does not explain how all this came to him. It mentions the lifting of barges, experience working on the river, and self-education. There are no calculation methods, which were lacking for Army engineers, in this biography. This is not an accusation. It's a blank spot. Just like with the Chicago Jacks. Just like with the buyers of Whitworth cars. The bridge turned out to be such that it has stood for 150 years. Here's a detail that is almost never mentioned. When Eads was designing the supports and realized that he needed to descend 38 meters to the bedrock, he could have chosen a simpler route, placing the supports on the riverbed. That's exactly what the competitors suggested. It's cheaper, faster, and technically easier. Eads insisted on the rock. The result? The bridge will stand for another 100 years, after most American bridges from the same period have long since been replaced. 38 meters down is an excess of reliability. The same characteristic as all 8 projects on our list. 3 arched spans. The central one measures 520 feet. The material is steel. Not cast iron, not wrought iron. Specifically alloyed chromium steel, the properties of which the metallurgical tests of that time could not fully confirm. No one had ever built steel bridges on such a scale before. Because no one had been able to produce steel with the required characteristics in such quantities. Eads set a condition for Carnegie's mills. The steel had to withstand a load of 20,000 pounds per square inch. Carnegie said it was impossible. Eads insisted. The mills restructured the process. The steel was produced. The industrial metallurgy of the United States made a leap that would have taken another 20 years without this order. The bridge supports go down to a depth of 38 meters to the bedrock. Workers labored in caissons, sealed chambers under compressed air. They ascended too quickly. Decompression. The doctors did not understand what was happening. The physics of this process had not yet been described. 15 people died. 77 suffered severe injuries. They were called bends, named for how the pain twisted their bodies. The arches were assembled without scaffolding in the river, using the cantilever method, where each span is built up from both banks toward each other. A mistake in calculations, and the midpoint won't align. Everything will collapse into the water. Eads calculated correctly. The U.S. Army Corps of Engineers attempted to prohibit the construction. Their specialists, professional military engineers with academic backgrounds, argued that the arches would collapse under their own weight. IDS won the legal dispute. After the bridge was opened, he ran 15 locomotives, each weighing 50 tons, across it at the same time. The bridge did not budge. Professional engineers with degrees lost a calculation dispute to a person who officially dealt with the salvage of sunken ships. This is not a stroke of luck. It highlights a gap in the level of competence, favoring someone who, by official logic, shouldn't possess such expertise. Look at one technical aspect that usually goes unnoticed: decompression sickness, the condition that killed and crippled the workers of IDs at a depth of 38 meters, is the physics of gases under pressure. Nitrogen dissolves in the blood at high pressure. When ascending rapidly, it forms bubbles. This is pain. This is paralysis. This is the end of the road. IDs witness this every day. The doctors did not understand what was happening. Science had not yet described decompression sickness. But IDs did something important. He introduced a slow ascent rule for certain workers and recorded the results. Without understanding physics, just through observation, the number of accidents decreased. IDs empirically discovered what physics will explain in another 20 years. This is not the intuition of a river diver. It is systematic observation with data recording. It is the scientific method without an academic education. Now look at what IDs passed on to the next generation. Not just metallurgy, not just caisson technology. He passed on proof. A complex project without precedent can be realized if one insists on the right foundation, literally and metaphorically. A rock foundation as philosophy. 38 meters to solid rock is not overkill. It is a principle. A principle that 20 years later Baker and Fowler will replicate when designing the supports for the bridge over Fort. They too will go deeper than the minimum calculations require. The Fort supports also rest on rock. And now we come to the final object, the one where all the previous lines converge into a single point. Scotland, Firth of Forth, the year 1882. The construction of the bridge begins. Before that, in 1879, the bridge over the Tay estuary collapsed during a storm. A train was crossing the bridge. 75 people lost their lives. It was the largest engineering disaster in Britain. The whole country demanded that the new bridge must be impossible to destroy. Engineers Benjamin Baker and John Fowler took the task literally. Before starting the construction, Baker did something unexpected. He conducted a public demonstration of the cantilever principle in front of journalists. He asked 2 men to sit in chairs and extend their arms. Each held a wooden stick with a support in the middle. The men represented the bridge's shore supports. Their bodies were the cantilevers. The wooden sticks were the truss beams. Baker then asked to place a third person on a beam suspended between the 2 pairs of sticks. This was the central span. All the load was redistributed onto the bodies of the 2 men and transferred down to the legs, to the bases of the supports. Visual mechanics. This is how a cantilever works. A photograph of this demonstration became one of the most reproduced engineering illustrations of the era. 54,000 tons of soft steel, 6.5 million rivets, 3 double cantilevers standing 110 meters tall. The total length of the bridge is 2,529 meters. The main load-bearing elements are steel pipes with a diameter of 4 meters, assembled from bent sheets right at height. Each rivet was heated to red heat, inserted into a hole, and then hammered out, on one side with a hammer, on the other with support, by hand. 4,600 workers at the peak of construction. Entire worker towns with libraries and schools were built for them. A temporary civilization that emerged for the sake of one structure and disappeared afterward. 73 people died. 8 years. From 1882 to 1890. And here is a detail that can easily be overlooked. The steel for the bridge over fort was supplied by factories that were already adept at producing chrome steel, the very type that IDS insisted on for his bridge over the Mississippi 20 years earlier. The metallurgical leap that IDS mandated in St. Louis directly made the bridge over fort in Scotland possible. One project laid the foundation for another. Across the Atlantic, 20 years later. Now, here's what's important. During the connection of the central spans, when two cantilevers, approaching each other from opposite banks, had to meet at a single point, the deviation was a few millimeters. On a structure weighing tens of thousands of tons, over a distance of kilometers, the deviation, just a few millimeters. A few millimeters. It's not luck. That's not how luck works. Look at how many factors need to be managed simultaneously. 8 years of construction, thermal expansion of steel. Every 10 degrees of temperature changes the length of a steel section by hundredths of an inch, which at a distance of kilometers translates into inches. Wind load on the enormous lattice surface over the open bay, variable, unpredictable, lateral. Clearances in 6.5 million riveted connections, each contributing a microscopic error. Uneven settling of supports on the bay floor over 8 years. All of this had to be compensated for, not at the final connection, but from day one. Otherwise, at the meeting point of the two cantilevers, there would either be a rupture or a collision. But the bridge stands. For 135 years. Hundreds of trains pass over it daily. A UNESCO World Heritage Site. It has preserved 99.5% of its original steel to this day. And what is shocking about this result, if you think like an engineer instead of a spectator, is that Baker in 1882 could not model wind loads on a lattice structure of this scale on a supercomputer. Such computers did not exist. Neither did sufficiently advanced aerodynamics. He tackled a problem that the next generation of engineers would explain 80 years later. By what specific method is unknown. The bridge did not budge. The bridge over the fort is the climax. It brings together everything that came before. Whitworth's precision. Without a standard thread, 6.5 million rivets would not be identical and thus unreliable. Brunel's tunnel principle. Understanding that work can be conducted in controlled conditions underground and underwater. IDS metallurgy. Siemens Martin steel. The first mass application of which took place right here. Hydraulic presses used in construction alongside manual labor. The very hydraulics that were already pumping water under London at 55 atmospheres. The scale implies the existence of a vast logistical and manufacturing base offstage. A whole temporal civilization emerged, achieved the impossible, and then dissolved. But here's what's remarkable. 4,600 workers at the peak of construction. That's a small town. These people needed to live, to eat, to have medical care, to have mail, to have stores, to have schools for their children. All of this was built next to the construction site. And after the work was completed, it was dismantled. No traces left. No maps. No documentary legacy of these towns. Only the official history of the bridge construction itself. 73 people died. Their names are in official documents. But where they lived, what they ate, how they received their salaries, who managed their household. This is not recorded anywhere in the same way that usual administrative history is documented. It's the same kind of gap in the records as with the manufacturer of jacks for Chicago. Let's now look at all of this together. 8 objects, different countries, different decades, different official functions. A car in Manchester, a tunnel in London, a telescope in an Irish bog, a raised city in America, pneumatic tubes under London, a hydraulic network, a bridge in Missouri, a bridge in Scotland. What do they have in common? All of them are made with a margin. The Whitworth measuring machine was more precise than any manufacturing of that time required. The tunnel under the Thames was financed by the government for 18 years without a single day of commercial return. Lord Rosse's telescope was more powerful than the astronomical challenges of the era dictated. The jacks in Chicago were standardized as if they had been produced in a factory about which no records were left. The pneumatic tubes under London had a capacity greater than ever needed by the Postal Service. The London Hydraulic Power Network operated for 94 years and survived 3 technological eras. The IDS bridge required the creation of steel that even the manufacturers deemed impossible. The bridge over the fort was designed with a precision for which no necessary equations existed. At first glance, it seems that they are just lone geniuses who were ahead of their time. Brunel, Whitworth, IDS, Baker, great engineers. Their courage, their intuition. But intuition does not explain 6,000 identical jacks. It does not explain the thread standard that simultaneously regulates production worldwide. It does not explain the hydraulic network that, in 100 years, will turn out to be perfectly suited for fiber optics. It does not explain the tunnel that the state funds as a national priority, even though there is no commercial return. Courage is a personal quality. But here we see something systemic. There is one more detail that changes the perspective. Several of these people knew each other personally. Whitworth worked with Maudsley. Brunel's son was friends with several prominent engineers of his time and was part of the same professional clubs. Baker, who built the bridge over the fort, consulted with contemporaries who worked on other projects of ours. This is not evidence of a conspiracy. It's just a fact. The engineering community in Britain was small. A few hundred people in the same clubs, at the same exhibitions, in the same professional societies. In such a community, information spreads quickly. A task set in one place can subtly influence decisions elsewhere. A standard adopted in one club becomes practice for the next generation. This is not a conspiracy. It's a network. The difference is crucial. A conspiracy requires a secret coordinator and conscious concealment. A network operates through shared values and common standards, without a central office, without a documented plan. The result is the same, but there are significantly fewer traces. This is what the network looked like specifically. In London, since 1818, there has been the institution of civil engineers. By 1850, it had about 2,000 members. However, the actual core, those who were awarded large government contracts, sat on selection committees and reviewed projects, was significantly smaller. Just a few dozen people. They met regularly, published reviews for one another, and recommended each other to clients. Whitworth was a member. Brunel's son was a member. Baker, who built the fort, was a member and eventually became its president. Fowler, the fort's second engineer, was also a member and likewise became president. In such a community, there is no need for an order to do this. It is sufficient to share a common understanding of what constitutes good engineering, what it means to have the right margin of safety, what it means to have a reliable foundation, what it means for a system that will endure the next generation. These criteria are not transmitted through documents. They are passed down through apprenticeship and professional authority. Each of these objects has what can be described as a second role. The official function is one thing. The real significance is another. A tunnel is formally for pedestrians, but in practice, it serves as proof of a principle that has altered military planning. A telescope is officially for astronomy, yet it effectively acts as a laboratory for mastering paraboloid surface technology. A hydraulic network is formally for elevators and cranes, but in reality, it represents an architecture of distributed power that has withstood everything, and later transformed into a cable channel. The jackhammers of Chicago are formally for sewage, but they actually demonstrate that urban development is not static. It can be raised, moved, and changed. Look at how each object becomes the foundation for the next. Maudsley trained Whitworth. Whitworth established the standard. The standard made it possible to mass-produce jacks for Chicago. Brunel's tunnel proved the principle of underwater passage. The principle was used by the metro construction. The metro ran beneath the same streets where pneumatic tubes already lay. The caisson technology that IDS developed on the Mississippi became the method for the supports of the bridge at Fort. The metallurgy that IDS was forced to create provided the steel for that very bridge. The hydraulic network under London during the construction of the Tower Bridge supplied the presses that shaped the steel sheets for its towers. And now pay attention to this. Each of these objects shares something in common, in that we don't know certain things about them. We don't know who exactly bought Whitworth's measuring machines and for what industries. We don't know who specifically insisted on the national significance status for Brunel's pedestrian attraction. We don't know how exactly Ross's technology transitioned to the military optics of Grubb. We don't know who manufactured the jacks in Chicago. We don't know why the pneumatic pipes were left lying around. We don't know whether there were clients for hydraulics who are not listed in the company's official reports. We don't know the source of IDS's calculation methods. We don't know what happened to the towns and people that disappeared after the construction of the Fort Bridge. These are 8 white spots, one for each object, in different countries, in different decades, of the same shape. The white spot of the same shape is not a coincidence. It is structure. Pay attention to what exactly is disappearing. Not the biographies of engineers. They are well documented. Not the technical descriptions. They are also available. What is disappearing is one specific link. Who exactly commissioned it? Who exactly funded a particular stage? Who exactly insisted on inflated parameters? Whitworth is known. His measuring machine is described, but the list of buyers is cut off. Brunel is known. The tunnel is described, but there's no documentation on who insisted on the status of national importance. IDS is known. The bridge is described, but the origins of the calculation methods remain unknown. These are not random archival gaps. This is a persistent absence of precisely one class of information, the source of the task and the source of competence. The history of technology focuses on names, on the geniuses of the era, But genius is, by definition, inexplicable. This is convenient. It eliminates questions about the system, about the foundation, about who exactly accumulated knowledge of unstable soils before Brunel arrived with a ready-made shield, about where the self-taught Ides got the calculations that army engineers lacked, about how production methods from an estate in the Irish bog found their way to military optics. There is another question that is usually not asked. In each of the 8 cases, the technology solved the problem on the first try. It didn't improve gradually, it just solved it. But what happened to the people who did this? Whitworth lived a long life and became wealthy. Brunel's son did too. Ides as well. These are not the people who are sidelined once they have fulfilled their role. These are the people who are released after the technology has already been established as a standard, a principle, an infrastructure. After the knowledge has been transferred from the individual to the system. And this is the quietest part of the whole story. The 19th century is not an age of progress. Progress is when you move from the simple to the complex, from the weak to the strong, from the imprecise to the precise. But here we see something different. Here, the complex appears all at once. Precision comes fully formed. Systems emerge fully mature. This is not progress. This is deployment. Look at what was included in this set. The standard thread is a unified production system across 4 continents, where any part is compatible with any other. The tunneling shield is a technology for protected corridors beneath any city and any strait. Parabolic optics form the foundation for long-distance communication and observation in any conditions. The serial jack demonstrates that urban development is not static. It can be lifted and relocated. Pneumatics enable rapid underground movement without leaving traces on the surface. Hydraulics create a distributed power network with a single switch for an entire city. High-strength steel allows for bearing structures of a new scale. Cantilevers provide spans without intermediate supports over any body of water. Each of these technologies, at the time of their emergence, seemed like a solution to an isolated problem. Together, they encompass the entire framework: what is produced, how it connects, what moves underground, who controls the switch, and what stands over any river. This is not a collection of breakthroughs. It is an infrastructure kit. And each element of the set has something that cannot be erased. Whitworth left a standard, embedded in every thread of every bolt. Brunel left a principle, reproducible under any river in any country. Ross left the technology of the parabolic surface, which transitioned into military optics without public announcement. Chicago left an underground layer, a city beneath a city. Pneumatic tubes remained lying around, ready for another application. The hydraulic network became a fiber optic line. The IDSA bridge left metallurgy, which it compelled to be created. The Fort Bridge left an understanding of what a structure calculated by mathematics that does not yet exist is. Documents can be extracted. An engineer's biography can be rewritten. An archive can be closed. But the tunnel under the Thames, which is still in use, cannot be removed. The Whitworth threaded bolts from thousands of old machines around the world cannot be taken out. The pipes that Mercury Communications has already filled with fiber optic cannot be closed. The material trace is the only one that cannot be retrospectively edited. Potential is activated only when a task arises, and a task appears only when it is set by someone who knows that the potential already exists. The hydraulic network became a fiber optic route not because Mercury Communications accidentally discovered pipes beneath the city, but because someone was deliberately searching for ready-made infrastructure and found exactly what had been built with the necessary reserve 100 years ago. Who is laying the groundwork for an unknown task? The one who knows her. Now the last question. Not rhetorical, direct. If we assume that before us are not 8 random breakthroughs, but a detailed set, then what exactly did the 19th century represent? Not an era of progress from simple to complex, but a period when someone methodically laid the foundation for the tasks of the 20th. Who exactly is not recorded in the protocols, but the task is evident in the material. Control over what is produced, over what moves, over who holds the switch. Take another look at this list. Thread standard, underground corridor, parabolic optics, series jack, pneumatics, hydraulics, high-strength steel, cantilever. This is not a description of an era of invention. This is a description of an infrastructure management system, established before the tasks for which it was needed even arose. Maybe it's a coincidence. 8 times in a row, in 2 countries, with the same handwriting, with the same white spots in the documents, with the same stock that turned out to be needed exactly when the next owner appeared. The objects stand. The pipes lie. The standards work. These are the only documents that have not been lost, and could not be lost, because they are made of metal and stone, not paper.